Alright, we're going to chat about the periodic table. Before we do that, just a real quick peek again at Dmitry Mendeleev. So this is the OG of the PT world. What he did is he put together this organization you see right here. And so the power of his periodic table wasn't the fact that he organized the elements according to properties and masses and things like that. Instead, it was the fact that he made predictions. So you see little empty spaces on his periodic table. What Dmitry Mendeleev did that was so remarkable is not only did he create this periodicity, so this repeating pattern that we see, but he said, hey, there's no element here, but it's not because it doesn't exist, it's because you haven't discovered it yet. And so he was able to predict what the elements would look like, how they would behave, what some of their properties are, just based on his periodic table. And because he made those predictions, and then eventually those elements were discovered and they matched his predictions, it made his actually stick, and it's still the format that we use today, and his is the name that we accredit it to. Right, and here is the whole periodic table. So we've talked about how it can be broken up into groups and periods. It can also be broken up into families, and so these different colored areas that you see all represent different families. And so just like this group right here all has 2 valence electrons, those 2 valence electrons means they react similarly. The elements where they kind of are in relation to each other also makes a difference on how they behave. Alright, so we'll go through them one at a time, look at a couple examples, and just get some ideas of what the properties are of each group. So the first group is the alkali metals. It's from lithium down to francium. Notice that hydrogen, even though it's above lithium, is not considered an alkali metal. So alkali metals are soft, silvery colored, they're very reactive, and they're never found in nature in pure form. They're never found in pure form because they are very reactive. They react with water, moisture that's in the air, or rain, and so if there was a pure sample of it out there in nature, it would react instantly and no longer be pure. Next are the alkaline earth metals. So the alkaline earth metals are soft, silvery white metals. They're a little bit reactive, although not as much as the alkali, and many of them are found in the rocks in the Earth's crust, so they're very, very abundant. Things like calcium, that's calcium carbonate that's in limestone. Beryllium is found in a lot of gems. So these are very, very common to find, reacted or bonded to other things in rocks. They're also very, very common to see in fireworks. So the different colors that we get from fireworks are due largely to the different alkali metals. So each alkali metal produces a different color. So like calcium is going to give you an orange color, strontium is red, magnesium is a bright white, barium green, and this is radium, which is radioactive. Next are the transition metals. These are probably the most recognizable of all elements, several of them at least, because of their properties. So they're down farther than everything else in the periodic table. They're actually part of what's called the B block of elements. They don't have a very stable number of valence electrons, or it differs from element to element. And as a result, they have some very, very useful properties. They're good conductors of electricity. That means electricity can flow right through them. Think of like copper that's in the wire in your house. They're malleable, which means they can be bent and hammered into wires and sheets, so they're shapeable. You know, if you take something like calcium and you try and bend it or shape it, it breaks. Okay, it's very brittle, whereas these guys right here, okay, they are very malleable. That's why we can take things like copper and stretch it into wires and use it to power our homes. So if you look through these, you're going to see a lot you recognize. Iron, copper, zinc, nickel, silver, gold, mercury, platinum, all kinds of elements that we use a lot. And their properties are very, very handy to us. Next up is the poor metals. So the poor metals, they share properties of the metals, so they're still malleable, they still conduct electricity and heat a little bit. However, they're weaker, they're softer, and they have lower melting points than the other metals. So think of like aluminum that we use to make aluminum pop cans. Think of how easy it is to crush an aluminum can. Imagine if that can was made out of something like iron, okay? It would be a lot thicker, a lot tougher. And that's because aluminum is a poor metal in that it's weaker and softer than the other metals. So here's a couple of the weaker metals. One is gallium. So gallium actually melts right around room temperature, about 85 degrees Fahrenheit. So in a warm room, it would turn into a liquid. So there's your lower melting point. Aluminum, like I said, it's really easy to crush. It's a lot softer. That's how we use aluminum foil. And then lead. So if you've ever gone to a dentist, they'll put a lead apron on you. That's to block radiation. Think of how easy that thing moves. You know, next time you're at the dentist, go ahead and grab it, see if you can bend it. And you can, because it's a poor metal. All right, so now moving on to the metalloids. So the metalloids aren't really a family of its own. Instead, it's kind of a double booking. They're elements that behave like metals and nonmetals at the same time. And so you can notice like germanium and antimony, they were on with the poor metals, and they are poor metals, but they're also metalloids. And so metalloids, they share properties with both metals and the nonmetals. So they kind of conduct electricity, kind of don't. They're kind of malleable, but kind of not. So they really share properties of both. As a result, things like silicon and germanium are very, very important semiconductors. So any digital electronics that you have semiconductors in them. If they did not have the properties of metalloids, they wouldn't work like they need to, and we would not have any digital electronics that we do today. So metalloids are right here, all microchips, things like this that you're seeing, all of those are made from silicon, germanium, or some other metalloid that's a semiconductor. Lets some electricity through, lets others not through. So as a result, we can keep things like bytes running on our computer. The mere fact that you're watching this video is owed to the metalloids. And now the nonmetals. And you're going to notice some nonmetals like silicon, it's also a metalloid, so it's double booked there. The nonmetals also include hydrogen. Even though it's over with alkali metals, it's considered one of these guys. They are brittle, they do not conduct electricity, and some of them are gases at room temperature, like nitrogen and oxygen would both be gases at room temperature. A couple quick examples of ones you would see. So this right here is graphite, which is carbon, so like pencil lead. This is nitrogen, it's liquid form, so that's about negative 100 degrees Celsius. Here's sulfur and phosphorus, that's found in match heads. Something cool about carbon, so carbon, depending upon how it's arranged, the carbon molecules, makes a difference in how it behaves, or how we perceive it, how we use it. So pencil lead is made of graphite, and so if you look right here at this structure, so that's just carbons making little rings of 6 carbons and then kind of layered on top of each other. When they're arranged like that, it forms pencil lead. When they're formed into more of a repeating structure like this, where everyone's attached, it creates nanotubes, which is what we use in carbon fiber bikes. So like really, really lightweight bikes are made of carbon as well. So the same thing that makes pencil lead also makes bikes, patches for the heart, and diamonds. When they're arranged more like this, you get diamonds. So beautiful luster, very expensive, all depending on how carbon is arranged. All right, group 7A, so these would be the non-metal halogens. So most of them are poisonous. They are fairly reactive. So these are kind of the counterpart to the alkali metals. These all have 1 valence electron that they want to get rid of. These have 7 valence electrons and want to gain 1 more. And so as a result, they'll do anything to gain that electron, which means they're pretty reactive. Something cool about the halogens, they are the only group on the periodic table to have all 3 states of matter. So you're going to find solid iodine, liquid bromine, and gaseous chlorine and fluorine at room temperature in the halogens. The noble gases. The noble gases are unreactive. They have 8 valence electrons except for helium, and so as a result they're stable, they don't want to react with anything else, and so they're gases at room temperature, and we use them actually lights. So the different colors that you see on lights are actually due to the noble gases. So when you see what we call a neon light, the only neon that's in there is the orange-red bulbs. The different colored bulbs that they get are due to the different noble gases that they use. So like pale lavender would be argon, helium would make a peach color, krypton silver, and xenon gives you kind of that pale deep blue. So here they all are, and this is actually pretty cool because next time you're out driving around and someone says, hey, look at that cool neon light, you could say, actually, friend, that's not just neon in there. There's argon, xenon, helium, krypton, depends on what colors you see. Your typical open sign usually has kind of a reddish open like that, but then there's a blue rim around it. It's probably argon that's making that rim. And last are the Lanthanide and Actinide series. So the Lanthanides would be the top of this bottom row down here. And the reason that row is down there isn't because they're really that special. It's because they're supposed to go right in here. So if you look 57 and 72, so 57, 58 through 71, and then 72 starts right there. 89, 90 through 103. 104 is right there. So if they put them right there where they're supposed to go, the periodic table will be too wide to fit on a sheet of paper. Anyway, these guys are shiny, they're very reactive. Most of them are also radioactive. And then the actinides, so same thing, taken out because it'd be too wide. These are all radioactive and very, very unstable, which means they do not exist in nature for very long. They have to be bonded to something else, or they'll decay, radioactive decay, into something more stable. And so that's it. Now, hopefully your periodic table that you guys have matches these colors now. If it doesn't, get yourself a set of colored pencils and color it in so everything looks the same as this one. That way we can kind of visualize the differences on the periodic table.